Welcome back to The Explainer. If you're looking to just bypass all the fluff and get straight to the actual mechanics of how modern tech is being pushed to its absolute limits by independent creators, well, you're in the exact right place. Today, we're diving deep into a massive, community-driven tech zine called Paged Out, Issue 8. Now, this isn't your standard, dry tech manual. No, this is raw, unadulterated grassroots innovation. We're going to unpack some incredibly dense topics by looking directly at the architectures and algorithms that these hackers and engineers are actually building. All right, let's just dive right in.
Just take a look at this futuristic cover art by Amir Zond. It perfectly captures that ambitious underground hacker zine vibe of the whole project. But honestly, the really crazy part is the milestone it highlights. Paged Out literally just crossed 1 million total downloads. As the editor-in-chief, Aga, mentions in the foreword, that number is high enough to fry a bot forward. And it's just going up every single day. There is a massive, undeniable appetite out there for this kind of unfiltered, deeply technical knowledge sharing. Since this issue spans over 90 pages, we're going to rapid-fire our way through 5 totally distinct concepts. We've got generating game worlds, the compiler revolution, PyTorch memory optimization, multimodal game agents, and finally, phishing autoencoders. All right, kicking things off with Section 1, Generating Game Worlds. So, a constraint-based tile generator, or CBTG for short, is basically an algorithm that tries to build a map by looking at a grid and deciding exactly which tiles can legally sit right next to each other, based on a set of predefined rules. It's kind of like a giant, complicated puzzle. You might actually be familiar with wave function collapse, or WFC, which is pretty famous for doing this. But as author Zeeves Zizak points out, WFC suffers from what's called contradiction sensitivity. Basically, if it hits a dead end where no tile fits, boom, it has to restart the whole thing entirely. But breakout model synthesis, it elegantly improves on this. Instead of a hard reset, it uses something called stochastic backtracking. It softly reverts just a localized little region around the error to a previous state, essentially reusing the successful work it already did, and then just tries again. So what does this actually look like in practice? Well, when generating something like a Pac-Man maze, the algorithm can soften and backtrack its way out of a contradiction without throwing away the rest of the perfectly good maze. And when applied to retro platformers or top-down RPGs, it can pump out fully playable, locally correlated levels. By fixing errors locally instead of globally, this algorithm is an absolute game changer. It allows indie devs to generate massive, playable configurations with basically zero setup. Moving right along to Section 2, the compiler revolution. Author Thunderseed outlines this really fascinating micro-narrative of the old way of doing things versus the new way. For literally decades, we relied on batch compilers. You know the drill. You ran your code, it went through this very strict pipeline of lexing, parsing, type checking, and if it hit even one tiny syntax error, yep, the whole pipeline halted and you had to start completely over. But modern languages, things like Rust, Swift, and Kotlin, they're using query-based compilers. Now, instead of running that entire massive pipeline, your IDE simply asks the compiler a targeted query, like, hey, what's the type of this specific variable I'm pointing at? The compiler then goes and fetches just that piece of information, so an error in one isolated part of your code doesn't block queries in another. This incremental compilation is the exact reason modern IDEs that run the language server protocol feel so incredibly lightning fast and responsive today. Next up, Section 3, PyTorch memory optimization. Okay, so when PyTorch builds a computation graph for your machine learning model, it has to make a critical decision. Which operations does it actually save in memory, and which does it just recompute on the fly? Because, as we all know, RAM is severely limited. Historically, as author Gendre Machan notes, PyTorch used a dynamic programming approach to the classic 0-1 knapsack problem to figure this out. The problem with that? Well, to get a result, you have to allocate a massive 2D table, sized by the number of items, multiplied by the max weight. It is incredibly memory hungry. And worse, to actually find out which specific items you chose, you have to painfully backtrack through that entire giant table. To fix this massive bottleneck, a PyTorch engineer named Horace He suggested 2 really clever tricks. First up, the sliding window trick. Instead of storing that whole gigantic 2D table, the algorithm just sort of slides over it, storing only the current row and the previous row. Simple, but highly effective. Second, to solve that annoying backtracking issue, they applied the Hirschberg algorithm. This is a divide-and-conquer approach, kind of similar to Quicksort. By splitting the problem into much smaller chunks, they eliminated the need to backtrack entirely. When you combine these two mathematical optimizations, it actually reduced PyTorch's peak RAM usage in this function by 20 times. I mean, that is just a staggering efficiency gain. Let's jump into Section 4, Multimodal Game Agents. So we all know large language models can write code and generate text, sure. But can a multimodal model, one that actually processes visual images, navigate a really complex 3D environment like Cyberpunk 2077 or Watch Dogs 2? Authors H. Emblem and R. Dosanjh decided to find out. Looking at how the agent room architecture is actually set up, first, we've got our inputs, actual raw screenshots of the game, along with the in-game minimap. These images are fed directly into massive multimodal models like GPT, Meta's Llama, or Anthropic's Claude. The model is then prompted to output a very specific three-part command: what controller button to press, exactly how long to hold it down, and, most importantly, its reasoning for doing so. That text is then sanitized and pushed through telemetry directly into the game itself. Now, actually making this work required some brilliant engineering workarounds. For instance, because the team didn't have a high-end gaming PC lying around, they actually ran the games on Xbox Cloud Gaming, using Python and Better xCloud to simulate the physical controller inputs. But here's the really fascinating part. They found out that if they only gave the AI a single screenshot, it would just get stuck, literally bouncing off walls like a confused Roomba. To fix this, they absolutely had to provide historical context. So they feed the model the current screenshot, the previous screenshot, and the last 5 movement decisions it made. Only with that specific history could the AI actually understand its own momentum and navigate the open world effectively. And finally, Section 5, Phishing Autoencoders. This right here is a classic data science problem. You want an AI to catch phishing websites, obviously, but your data set of known phishing sites is absolutely tiny compared to the millions and millions of legitimate websites out there. If you try to train a standard classifier on data that is this radically unbalanced, it just fails. Because it completely lacks counterexamples, a standard neural network is going to push its decision boundaries arbitrarily far to minimize its loss. This effectively means it starts overdiagnosing, labeling things it has literally never seen before as phishing. So, the solution? An autoencoder. Instead of training the AI to make a rigid yes or no classification decision, it simply learns to compress and then reconstruct the data. The author vectorized the text of legitimate domains, which is essentially just looking at the frequency of different letter combinations, and trained the autoencoder purely on that normal, safe data. During inference, when a new domain pops up, the autoencoder tries to reconstruct it. If it's a weird, anomalous phishing domain, the network is going to struggle, which results in a really high reconstruction error. You then simply flag the domains with the highest errors. It is such an elegant way to spot anomalies without needing a perfectly balanced dataset.
Which really brings us back to the sheer scope of the paged out community. As project lead Ginval notes, issue 8 is their absolute largest so far, proving that, hey, setting firm deadlines really is a fantastic way to motivate people. But honestly, it's a true testament to the raw volume of independent grassroots knowledge that's out there. Just think about it. In a few short minutes today, we've bounced from algorithmic game design to compiler infrastructure to AI memory optimization to LLM game agents and finally to cybersecurity autoencoders. And all of this came from a single, free, community-driven zine.
Which leaves us with this final thought. The gap between massive enterprise-level tech and independent grassroots experimentation has literally never been smaller. The tools, the algorithms, and the deep insights are all entirely out in the open, being shared freely by incredible communities like Paged Out. All this knowledge is sitting right there, just waiting for you to pick it up and use it. So with all of this at your fingertips, what are you going to build next? Thank you so much for joining me for this explainer, and as always, keep learning.